Data to and from space. Using a Rockblock module, part 1 of 3, today on Mikey's Lab. Hi, and welcome back to the lab. If you haven't already, go ahead and hit that subscribe button down below to ensure that you don't miss anything, including parts 2 and 3, which will be coming very shortly, of our Rockblock hardware abstraction module. So, as we talked about in the previous video, the Rockblock is a very powerful module. It allows you to talk to the Iridium satellite network in a subscription-based, message-based type of a system. However, there are some traps for new players and things that make it more difficult to use than it needs to be. So what we're going to be doing today is we're going to be looking at the first part of the software, which is the software to send data to the Iridium network, and then it comes back to you via email or you collect it via web API from the website. And we're going to take a look at how to send data to space. Now in part 2, we're going to take a look at how to receive data from space, and in part 3, we're going to spin up a custom PCB with everything that we need to do this and complete our hardware wrapper layer for the Rockblock module. So lab code up. We're going to learn something today. Let's just take a quick peek at the hardware itself. We have our Rockblock module with our breakout header. We have several pins connected here, including the one that indicates when satellites are available. That is a very, very good piece of breakout that doesn't exist with the header that comes with this, so make sure that you buy the additional pinout header. We have another pin here as well that lets us put the module to sleep. That will allow us to get the maximum battery life out of our project. Now the Rockblock is a 3.3 volt device. The Arduino that we're using is a 5 volt Arduino because that's what I have in my lab. So we also have a level shifter, which will shift from the 5 volt output of the Arduino to 3.3 volts for the input of the Rockblock. It's very important. If you throw 5 volts to the Rockblock, I don't know what will happen. It might be 5 volt tolerant. I'm not risking a $600 module. It's just not going to happen. Let's go ahead and dive right into the source code. Okay, I'm going to be looking at my computer screen a fair bit here, so I apologize. If we look at this, at the source code itself, we'll start at the very top as we always do. For those that are interested, this is not the Arduino IDE, but this is written in Arduino. I'm using a Visual Micro plugin for Visual Studio, which allows me to program the Arduino inside of Visual Studio, which by far is probably the best IDE on the planet, and I am not a Microsoft fanboy by any means, but they did very well with this IDE. So at the top you see the two standard includes of wire.h and software serial.h. The wire.h is there because eventually we want to make this an I2C or serial wrapper so that the project that's talking to this device can speak either I2C or serial. Right now the wire.h is not required. Software serial is because that's what we use to talk to the module. The next thing we do is we declare a Rockblock message, and we set up the message queue. So if we go over to data structures, you can see we've defined what a Rockblock message is. Now this is new for a lot of my projects. I don't break out this way, but given the complexity of this and the memory management that I wanted to do, this was very important. So we have a byte array for queue time, which is 2 bytes, which will include hour and minute. We have the message type, which is just a numeric representation of is it a binary message or is it a text message. We have a char array, which is the message itself, and we have a status of the message. The status flag, when we go through queue management, you'll see where the status flag comes in, and it lets the wrapper know what is going on with that particular message. Has it been sent? Is it sending? Is it waiting to send? So we go back and we declare software serial with the RB pins and the TX pins and the RX pins for the Rockblock. If we go over to our test.h here, you can see that we have defined these inside of that header file. Again, I know I don't normally use header files with my software, but this is going to be a very complicated piece of software, so it makes it a little easier to work with, but it makes it a little harder for me to explain to you. So then we decide that we want to have a global variable for the last interrupt that we've called, a global variable for the last send attempt. The reason we want the last send attempt is we want to throttle how many times or how fast we attempt to send to the module. And we have an unsigned log for the last time we've used the module in any way. This is used for putting it to sleep. So we enter the setup run like we usually do. First thing we set up is the serial. Right, so we'll just shoot down to the setup serial function. Right, and serial begin 57.6, which is the serial between the external device and the Arduino, and then we set up the soft serial, which we call SAT, at 19200, which is the baud rate that the Rockblock is expecting us to use. From there, we go back up and we set up the pins. This is basically setting up pin modes. So the sleep pin we set to an output. Obviously we want the Arduino to talk to it. The satellite pin we set as an input. That is a pin that changes state based on whether or not a satellite is visible to the module. And then the test pin we set as an input because it's going to be a button. Right, then we proceed to set up module, where we send a command to the module using AT-E0, which tells it I don't want you to echo back to me what I've said to you. That makes it a little harder for us to communicate with parsing things coming back if it's echoing to us. This is one of the rare times in my code that I use a serial or I use a comment. Comments generally are left out for me, but it might be a little bit of a black box situation, so I went with that. Then we set up our interrupts, which is, for me, is just the test pin. So whenever the test pin changes, I want you to add a message to the queue. And then we tell whatever is connecting to this that the Rockblock 9603 wrapper has started up. From there, with any Arduino project, the next thing we enter is the loop. So the first thing we check whenever we do, we loop through the command, is have we reached the minimum time between transmits? So if we've set this to 30 seconds or 3 minutes or 5 minutes, however long we've set it to, which will probably be based on how fast those capacitors can charge in the system that we're putting this in, has that amount of time passed? Now you notice that we don't use a delay here. I generally don't like delays, so we're just going to use the millis of the last send attempt that we set the flag up at the top to 04 plus maximum time between transmit is less than the number of milliseconds that this Arduino has been operating. Now there are overflow situations where this could trigger early. My testing indicates it's not really that big of an issue because millis obviously will eventually overflow if this is on for a very long period of time. So next thing we do is we tell, this is more debug prints than anything for me. So we tell whatever is attached to our wrapper that we're about to do an exchange attempt, and that we're checking outgoing messages. So the first thing we do is we enter into the queue itself. We look at the first message, for example. We see, does it say that it's sent? If it does, we remove it from the queue. If it doesn't say that it's sent but it says that it's queued, we find out what type of message it is based off of that message type flag that I had indicated before. So if it's text, we call the send text message with the message ID. If it's binary, we call send a binary message. So let's take a look at the send text message. So once we've entered the send text message side of things, we print to the connected device that we're attempting to send message ID, whichever ID we are. Again, this is more debug code than anything. I'll put this into final practice, this probably will not be there. So we enter into a prepare to send function. If we go to definition for that, we make sure that the module is awake. So we have a function where if we haven't used the module in a little bit, we put it to sleep. When it wakes up, things need to go. So we send that we told the module to wake up, right? This, if we go to the wake up function, right, you see that we just set the pin to high, and we wait for however long we've determined that the charge of those 5 farad capacitors takes to go through. And we come back to the prepare to send function, and we call a function called turn off flow control. Go to definition. So we basically are sending an ATK0, which turns off the flow control between the communication of the module and the Arduino. We'll take a look at the send command, send to module at this point. So with the send command to module, because this module is all AT based commands, that means it takes a text string and it returns a text string, and we need to parse what happens to find out if it's okay. We're going to be doing this a lot. So proper coding structure says that we create a separate function that allows us to handle that in itself. I have set this to basically be the send command to module function, and we get a boolean back, true if it was successful, false if it was not. So the first thing we do is we create a character array called response, which is how much data are we expecting from the module in response to the command that we sent. So I've set this to be 100 characters. Then we print the command that we have sent to the send command function to the satellite module itself. We go into a function called wait5, which if we peek to the definition, tells us that basically we wait 5 seconds, and every second we print a dot just so that the world knows we're still paying attention to the module. So we go into a loop while sat is available and I is less than 99. We're going into the receive buffer of the software serial module for communicating with the module and seeing if it's responded yet. If data is available, and this is less than the 99th time we've gone and grabbed data from it, so remember our queue is only 100 characters, so we can only grab 1 character at a time. So what we do at that point is we add whatever we got to the response array, and once that's complete we go through. Now with most commands for this module, returning OK means that the command was successful, returning anything else means the command was false or failed. So we look using the stir function, which if you remember from any of my other videos is a way to look for a string inside of a string. Right, so we're looking in the res array for OK. And if it's not null, right, we return true. Now as part of the debugging code here as well, if it doesn't succeed, I want you to print the entire response back to me so I know why. This is, again, probably not going to make the final version, but when you're debugging this is very handy. And then we return false if it was not successful. So we go back to turn off flow control, which sends that command to the module, and we come back to if that was successful we continue, if not we return false. Next thing we do is we check for a network, which if we go to the definition for the check for the network, basically we read the digital pin that breaks out for us to tell us is this satellite available. This nomenclature is a little weird, okay? So digital read obviously returns a high or low, right? And we're equaling that to a high. So if the pin is high, if the pin is high, what's going to happen is we're going to return true. If the pin is low, we're going to return false because this statement is false. It's just a different way of typing it than a huge if statement. Makes it a little more condensed. Obviously, our debugging code then says that the network was not found and we return false. If it wasn't found, if it was false, we say network was found and we continue. Next thing we do is we check the module communication by sending AT to the module and make sure that it will respond with OK. That lets us know that this is awake, this is alive, this is happy, everything is working the way that we think it should be, and that the module is now fully awake. So we finished prepared to send. If we're continuing, we've obviously received a true since we have the not operation here. If we received a false, we put the message back in the queue. If we weren't able to send, we'll try again in the next iteration. If we were successful at waking the module up and we are prepared to send now, we have a car array 19 plus message length. Right, so the 19 is obviously the characters that we need to put in front of the message that we want to send as part of the AT statement for this module. So what we have here is we're printing into the message variable, into the message array, AT plus SBD WT. Okay, so we're going to write text. Right, we're using %D, which means that the first two variables are decimals. So message queue time and message queue time 1. As you remember, these are part of the message structure that we'd set up earlier. Right? And then dash and %s, which is the message itself. Now the timestamps that we're putting into here are not necessary. This is just a message format that I'm using. You can ignore them if you want. So basically what we're doing is the AT plus SWT equals, right, and then the message that we want to send, the text string that we want to send. Then we send the command to the module, which goes through that long process we've already looked at. And we enter into start SAT communication. So if we go to the definition of start SAT communication, we have the starting the actual exchange. Again, we have a response buffer that we've created before. This one is 200 as opposed to the 100 from before, because this is a more verbose response than we're expecting an OK from the other ones. So with SAT print line SBDIX, the IX starts the exchange. It's the AT command to the module to tell the module to start communicating with the Iridium network. We then wait 30 seconds because the module is going to do whatever the module is going to do. It's going to take a bit of time before it gets back to us and lets us know whether it was successful or not. Then once again we read the satellite available, very much like the other command that we sent, and we parse for a return code. Now we created a function parse for return code because what comes back is not straightforward. So what comes back is a collection of numbers, okay, and the numbers that come back, the very first one is the one we're interested in for this because it will give us a code telling us whether or not the transmit was successful or not. If you're unfamiliar, you can look at the other video that I did where I go in more into depth with that particular operation. So what we're doing is we're looking for the start character. In stir, we're processing the response that was sent to us, looking for plus SBDIX. So anything else that it sent, I don't care about. I want to get to the start of here. Right, and then we take the start and we add 8 characters. Why 8? Because 1, 2, 3, 4, 5, 6, 7. Right, so we want to move 8 characters into the message so that we get to the actual first digit of the first number of the response. And then we return A to I. Now, for those who have been with us before and have watched the video on why strings are bad, will know that the A to I function takes in a character array and converts it to an integer, stopping at the first non-numeric character it finds, which is really handy. Really, really handy. So if we step back then to the start SATCOM, and if it comes back with a true, meaning that the message was sent, we go ahead and print message sent, and we return the status of message sent. And then we go back to here, and you see that status of message sent then gets applied to the status flag in the message queue for the other one. So the next time we run through, we'll see that that one was sent. We'll remove it from the queue. Binary is a little different than text. So we'll dive right into the binary. So again, we have a 200 character response buffer and a 20 character message buffer. 20 character because 20 cars is 20 bytes. Attempting to send that binary message ID, again, this is all just, troubleshooting code. We go to the prepare to send to make sure that the module is awake and happy to go. If it isn't, we return message queued. If it is, we proceed. So we take the Rockblock message pointer and we grab the message itself. And then we look at the message, we define a variable message length by looking at the string length of the message. We take a look at the message size, which we do by taking the length of the message times size of character. Now the reason you want to do this, right now we're using an Arduino. Maybe next time we're going to use an ESP, maybe next time we're going to use a PIC. You cannot guarantee the byte size or memory size of a character. Because of cross-platform compiling and stuff, this just makes it bulletproof. So we're asking what the size of a character is on this particular compilation, and we're using that to determine the message size that we're sending. Then we do the sprintf that we've normally done, where we basically issue the AT command for this time WB write binary, and we insert %D, which is just the message size. Okay? And we send that to the module. Now we could have expanded our send command to module function in order to make this work, but because of the way binary is handled, this made more sense, and I would only ever be using it in one spot. So what we do again is we wait 5 seconds after we've sent it to the module for the module to be ready. Right? We check to see if we received a response. If we receive the response, ready. Right? We know that it's ready to receive binary data. Okay, so once we've received the ready, the next thing that the system, the Rockblock wants to receive is the message itself. So we write out the binary of the message itself. Then we move over 8 bits. We write the checksum as well. We wait 2 seconds, right, and we should receive a response of 0 and OK. Then we tell it to start the satellite communication. The 0 being a response to the checksum, the OK being a response to the module is willing to talk. Then we start the satellite communication, which is the exact same thing as the text transmission. For debug purposes, we print the message sent, and we return message sent. Otherwise, we return message queued because for whatever reason it failed. And we get back to the main loop. We set that we did a module action so that we know whether or not we can put the module to sleep. Right? We indicate that our last send attempt was now. Right? And we look at if our last module action was more than 300,000 milliseconds ago, meaning has it been several minutes before since we performed an action. If it's been 5 minutes since we performed an action, we're going to go ahead and put the module to sleep. Again, this is designed to be in a very long-running situation where battery power is incredibly important. So if we haven't used the module in 5 minutes, put it to sleep. And then we use a delay. Now I'm going to be doing a video shortly on delays. I don't like delays, but in this case it works quite well. We use the delay to throttle the loop function itself to make sure the loop can never run faster than once a second. But it will never run at once a second because everything else takes a significant amount of time to get through. And that's why delay is a little weird. Alright, so there you have it. I know it's not the most exciting topic or video that I've ever done. It's a lot of source code, it's a lot of theory. I tried to break this into 3 pieces, obviously, so that we don't have this massive monolithic video that's impossible for people to watch. But that is how, using a Rockblock 9603, you can send either binary data or text data to space. It is the first part in our hardware wrapper layer. Second part coming up very soon, which will be how to receive data from space. And then the third part will be the PCB layout of the embedded Arduino that ties all of this together and makes it one module that is much simpler to use than the bare Rockblock module provided by SparkFun. If you enjoyed this video, go ahead and give it a thumbs up. If you haven't already, hit the subscribe button, turn the notifications on, you know the drill. Thank you for joining me in the lab. I hope you learned something today, and we will speak again soon.